Imagine a theory that has stood unchallenged for a century suddenly being questioned. This is exactly what's happening with the long-held beliefs about the formation of the Himalayas. For the past 100 years, Émile Argand's theory has been the cornerstone of geological understanding regarding the Himalayan mountain range. According to Argand, the continuous collision between the Indian and Asian tectonic plates caused the crusts of both plates to thicken significantly, creating a super thick layer that supports the towering peaks of the Himalayas. However, recent research is challenging this long-accepted theory. Scientists have identified several issues with Argand's hypothesis, pointing out that a crust thicker than 40 kilometers would struggle to support a plateau as vast as Tibet. Argand's theory suggests a crust thickness of 70 to 80 kilometers, which seems implausible given the geological constraints. Over the years, skepticism has grown as more studies have uncovered contradictory evidence. For instance, geochemical and seismic data have revealed the presence of mantle rock in areas where it shouldn't exist according to Argand's model. This discrepancy has fueled further investigation into the true nature of the Himalayan crust. Now, a groundbreaking study published in the journal Tectonics offers a new perspective on the geological dynamics beneath the world's highest mountain range. The researchers conducted over 100 two-dimensional numerical simulations, varying the properties of the crust and mantle. By comparing their simulations with real-world seismic tomography and geochemical data, they developed a more accurate model of the crustal interactions. The findings suggest that instead of the uniformly thickened crust, the collision of the Indian and Asian plates likely resulted in a crust-mantle-crust structure. This means that a thin layer of the more rigid Asian mantle is sandwiched between the Indian and Asian crusts. The simulations also indicate that the Indian crust slid beneath the entire Asian lithosphere, including the crust and upper mantle. At these extreme depths, the Indian crust partially melted due to high temperatures, with some portions rising to the area beneath the mantle section. According to the study's authors, a more plausible mechanism for doubling the thickness of the Himalayan-Tibetan crust is through the viscous underplating of the Indian crust beneath the Asian lithosphere, rather than crustal thickening alone. In this scenario, the Indian crust provides buoyancy, while the Asian mantle offers the necessary strength to elevate and support the Himalayan-Tibetan topography. This new explanation aligns better with previous observations, such as the unexpected presence of mantle rock near the surface. Future research may explore three-dimensional modeling to provide even more detailed insights into the geological complexities of the region. This work not only enhances our understanding of mountain-building processes, but also has implications for studying other geological formations. The study's authors conclude, if our model is correct, it fundamentally changes our understanding of the dynamic mechanisms responsible for the creation of Earth's most majestic mountain range. It also reshapes the ongoing debate about the flow patterns within the Asian upper and lower crust, and the strength of the Asian crust during the formation of Tibet. This article, crafted by our author Crustal, edited by Lisa Locke, and fact-checked by Robert Egan, is a testament to the dedication of our editorial team. We rely on the support of readers like you to continue delivering independent science journalism. If you value our reporting, consider making a donation, especially a recurring one, to help us remain ad-free and sustain our mission. For more information, see the full study by P. Sternay et al., titled Raising the Roof of the World, Intracrustal Asian Mantle Supports the Himalayan-Tibetan Origin, published in Tectonics, 2025. 10.1009-2025 TC 0957.